Fritz from Vienna, and he will tell us about the red sequence.
Milano here.
Yes, I'm still. I'm coming from Vienna, that's
He's
true.
coming from Vienna,
But
now he is working
I'm still associated with Milano.
Milano. He will tell us about red sequence. I thought that red sequence is the Soviet Union, China, Cuba, North Korea. That's not the case.
Okay, thank you very much. First, I would like to thank the organizers of the seminar for inviting me and for giving me the opportunity to present some results I've been recently working on. It's a great pleasure to be back in Warsaw. I've just briefly visited Warsaw some months ago, and it's a great pleasure to meet you all and to meet the CFT. Today I will talk about galaxies surveys, and in particular about the VMUS Public Extragalactic Redshift Survey, which has this nice abbreviation bypass. And I will show you that by studying galaxy surveys you can not only constrain cosmological parameters, but you can also study galaxy evolution. And in particular, I will concentrate on early type galaxies, and these early type galaxies can be characterized by the so-called red sequence, which I will introduce later on. So just a brief outline of my talk, because maybe some of you might not be familiar with this topic I'm presenting. I will give you the basics and I will set the context I will be talking to you. And using these basics, we will immediately go to the motivation of my study. I will then focus on the main results we derive from the VMUS Public Extragalactic Redshift Survey, particularly on this red sequence. And I will spend most of my time on the interpretation of this data, and of course I will summarize the main results. And afterwards, in the second part, I would like to show you some other projects I'm currently involved in and some prospects for the future. So if you look into the night sky, you can see that galaxies are not randomly distributed. They are not actually randomly distributed, they are actually clustered. And this is just an example of the local galaxy cluster coma, where you can see this local galaxy cluster is dominated by early type galaxies, which are indicated here as these orange yellowish dots. It has been found from very detailed studies in the local universe that the majority of these galaxies are these early type galaxies, and in fact more than 50% of the total baryonic matter is actually locked up in these galaxies. So in order to understand the origin and the formation of the universe, we also need to understand how early type galaxies form. That means that we are actually having a very interesting and very important probe of the universe. So one way to classify early type galaxies is by classifying them according to morphology. And in the early 20s, Edwin Hubble has introduced this so-called Hubble tuning fork, where he just classified galaxies according to their morphological types. So on the left-hand side, you have early type galaxies composing of elliptical galaxies and lenticular galaxies, and on the right-hand side, you have late type galaxies. Here, there are only spiral galaxies shown, so irregular galaxies and starburst galaxies are left out in this diagram. What you can see is that early type galaxies are actually dominated by a spherical structure, and they have this very central intensity peak in the center, which is called this bulge. And this bulge component decreases if you go from left to right in this diagram, and for zero galaxies you have an additional component of a disk, whereas for zero galaxies you have just a disk component without any spiral arms, and if you go then to spiral galaxies you have not only this disk component, you have spiral arms, you have the dust component, and you have also young stellar population. So already by classifying them according to this relatively rough scheme, you can see that early type galaxies are mainly characterized by passive old stellar population, so by red colors. Whereas if you go to late type galaxies, you have a more complex stellar population, blue colors, and also star formation and dust. This is in the local universe, but if you go to higher redshift, I give you here two examples from early type galaxies at a redshift of 0.25, which is about a look back time of 3 billion years. And based on these two high resolution images from HSD, so this is the best what you can get, you can see that here is 1 arcsecond, and these galaxies are face on, so you look on top of them, you really cannot distinguish which of them are elliptically squared zeros. What you need to do is you need to decompose the surface brightness distribution, and you can see that elliptical galaxies are actually characterized by a so-called Lebeck profile in the surface brightness. So you have the surface brightness as a function of radius, and in this diagram you can fit the data points by an r to the quarter profile, whereas for lenticular galaxies you need an additional component, as I already mentioned, so this component to characterize the surface brightness profile. So of course, if you go to higher redshift, you need to understand how this bimodality in the colors evolves as a function of time, and you have different other effects. For example, the dust, what is the dust component in the galaxies, how does that evolve with time? And for most, it's very important to select a clean sample for your studies if you want to study galaxy evolution, because the types we see in the local universe might not be the same galaxy types which we see in the high redshift universe. So these so-called progenitor bias need to be accounted for, so probably there's a lot of merging going on in the high redshift universe, and you need to identify the correct types you want to study. So it has been shown very nicely in the local universe that actually the colors and the luminosity of galaxies are tightly correlated, and one of the most prominent scaling relationships are the so-called color magnitude relation, where you plot the average color here, the U minus B rest frame color, as a function of luminosity, or here I just plot the stellar mass of the galaxies, normalized by the solar mass. And you can see that in this diagram you can very nicely split already early type galaxies from late type galaxies. So these early type galaxies are actually very tightly correlated to a very narrow range in this diagram, which is in this range, and this is therefore called this red sequence. It's just that they are clustered around this area, and that's why we call this as red sequence. This red sequence has also been used to study, for example, galaxy clusters at higher redshift, because you can trace that to very far. Whereas blue galaxies in this diagram are really spread out here, they don't have any major clustering. And interestingly, you can not only correlate the colors and the luminosity and the stellar masses, you can also correlate the overall appearance, like I showed you before. So you see that elliptical galaxies have more this like roundish structure, actually boxy isofolds, that's just the distribution of the light intensity. Whereas if you go to zero galaxies, they are more elongated, they are disky, and spiral galaxies, of course, have these spiral arms and different morphologies. And at the same time, so the supermassive black hole is more prominent in early type galaxies, and the influence gets less for spiral galaxies. At high redshift, there have been also a few studies based mainly on small number statistics, and they have been coming up with different scenarios how to account for this evolution, how to build up this red sequence. However, most of these studies are not in agreement. They show a large scatter, and I have here plot all the results that have been found in the literature within this diagram. What I'm showing here is now this average U minus V rest frame color as a fixed luminosity at minus 20 in V band absolute magnitude as a function of redshift. And the different dots here are the different studies, different colors for the different studies. mentioned, and you see the error bars, which include not only the observed error bars but also the systematic error bars. And from this you already can see that these studies derive different results and different conclusions. That is due to several effects. Like I mentioned already, that there are low number statistics. Then some of these studies use different filter to select the galaxies, so the selection method also plays a role. Furthermore, most of these studies are really pencil beam studies, which means that they are probing a very narrow volume in the high redshift universe, and you don't know if this is representative for the whole universe. If cosmic scatter has an influence, there's also an effect which needs to be accounted for. And of course there could be incompleteness effects also. So the question which comes to our mind is, are these studies in agreement, and if there's really a coherent picture which we can derive. So our motivation was really to pin down when and how this red sequence has been formed. We want to base our study on a high sample statistics, so a large number of galaxies which is not subjected to sample statistics. And we want to explore different selection criteria in order to see how the selection criteria then affect our results which derive for the evolution. And for most, we also want to give a local reference for future studies, like for example for Euclid.
Excuse me, but I think this plot is pretty consistent. Why don't you like it? I mean, there is hardly a point which is off by more than 1 sigma, which can always happen, as we know. So, compared to the previous plot, which we used to define the red sequence, when there was a really big dot, so to speak, and you said, well, this defines the red sequence. This plot is pretty consistent. Much better.
It is better because it is in logarithmic scale. Because you should remember that this luminosity is logarithmic. And this is why it looks consistent. But
here it looks consistent. It's made to look consistent. But I just show you 2 examples when you just look at the green dots, and what you want to measure is here the local reference set up by this black dot, and you want to have a consistent evolution. So if you fit, for example, these data points with this line, this is very different to the one which you fit here, right? So it really depends, because here is a large discrepancy in the local universe that has many effects. It has always an effect where you measure this U minus V, for example, at fixed luminosity, or if you just assume a constant slope or a different slope in the relation of the colorimetry. I will come back to that. But it is not consistent, because the evolution you derive here is very small, so you need to have really a high precision measurement to pin that down.
The second question, I understand that there is an assumption that all the spirals, blue spirals, will finally end up as a red elliptics, right? But this is based on simulation, how do we know really?
It's based on simulations, yes. Mainly on simulation.
What is a typical time scale for Milky Way to become an elliptic galaxy?
Well, the merger with, now it's a spiral galaxy, so we cannot say if it has been previously an elliptical galaxy. It will merge at a certain, in about 3 billion years with Andromeda galaxy.
No, I understand, but the point is that elliptics are the result of a late evolution of spirals, right, or not?
No, it's not.
No.
So that was the previous assumption, for example, from Edwin Hubble, that it's an evolutionary sequence, but it's actually not. It's much more complex than that. You have lots of physical effects going on, and of course within the simulation you can merge 2 spiral galaxies to form an elliptical, but this is just one scenario. There are very different scenarios to form elliptic galaxies. I will come back to that in my interpretation. So in order to solve all these questions, we conducted a large ESO program, large observational campaign called the VIMUS Public Extragalactic Redshift Survey, where we used a very large telescope in Chile, together with the VIMUS optically multi-object spectrograph. And within this, with this instrument, you can obtain with one single observation a large number of spectra. So these are all galaxy spectra in 4 different pointings. So in the order of 330 to 400 spectra, depending on the area on the sky. So here just some numbers of the survey. So we have already over 440 hours obtained multi-object spectroscopy, even actually a little bit more. So we target 2 different fields in order to explore then the effect of the cosmic variance, and the total area we want to map is 24 square degrees. So this is an I-band selected survey, and the selection criteria, so we have multi-object photometry, and we select our spectroscopic targets using this R-E, U-G diagram, where within this color diagram you can very nicely split galaxies which are at lower redshift, lower than 0.5, which are indicated in blue, from the ones which are at higher redshift, indicated here with the red points. So within the selection we have this rough color selection, and then we have also a selection where we reject stars, and with our spectral energy distribution we also do not want to select interesting targets such as AGN, so we can recover actually the colors of them. So the total aim is to observe 100,000 galaxy redshifts with an average sampling of the whole survey and the whole area of more than 40%, which is pretty high for this survey. So to compare that to the local universe, so the 2DF Galaxy Redshift Survey, our survey is comparable to the number density and the volume probed, but of course our Galaxy Redshift survey is at medium redshift of 0.8. So here you see the first detailed view of galaxy clustering at high redshift. What you see here is a slice of the universe, so the 2 different fields, W1 and W4, where you start from the right hand, approximately at 0.5 in redshift, up to redshift of 1.5, up to a redshift of 1.1, which is approximately 5 billion years you can cover here. And each single point is a galaxy redshift measurement, and you can see very nicely, which has been shown in simulation but not in that detail at high redshift, that galaxies are clustered. So you have galaxy clusters, galaxy groups, and you also have regions, void regions, which are almost absent of any galaxies. So within this scheme you can very nicely study galaxy clustering, but of course also galaxy evolution. Just very briefly, the sample I've been using, here you see the redshift distribution of the total sample. So we go from redshift 0.4 to 1.3. So you see here the histogram of the total number of galaxies, which is about 45,000 galaxies, and the different types here are classified also, and the different numbers are also given. So we have a medium redshift of 0.7, and we have a high confidence level in the redshift measurement. So we are really, we really trust our redshift measurements, so we can use that as a very nice tracer. And you can see that the numbers split almost equally between the 2 fields. So for the analysis, I just picked up one part, which is the derivation of the absolute magnitudes and the stellar masses, which we will be using later on. So we are using the photometric redshift technique Hyper-C from Nicole Bolsonella, which is indicated in this diagram, where you observe the galaxies in different filters as a function of wavelengths, and you compare this observed flux here in black with the one predicted by the spectral energy distribution. So you do that by actually iteratively calibrating the 0 points, and that can be much more accurately done with spectroscopic redshift than if you're using just photometric redshift, because the errors are much smaller. So within this technique, you're not only using here, like I show here, the optical part, but also the near infrared up to the Spitzer photometry, so we have really a multi-wavelength photometry. That means that our K corrections are really small, and we can derive very accurate absolute magnitudes and stellar masses. So the total uncertainties are in the order of 4 to 10%, and at the highest redshift bin it's a little bit higher, which includes all the systematics. And we use then also the Calzetti dust extinction laws and the pivot extinction curves to account for the dust extinction in our galaxies. So the first results, I want to show you the color magnitude relation for vipers. What you see here is again the U minus V rest frame color as a function of absolute V bank magnitude for different redshift bins. So we have the redshift bin 0.4 to 0.5, 0.5, 0.6, and it goes on up to redshift of 1.0 to 1.3. The color coding is just representative for the different galaxy types. So you have early type galaxies which are indicated as red, S0 and B galaxies indicated with green, and then spiral galaxies and starburst irregulars indicated with blue and magenta respectively. If you make just a rough cut in U minus V at a fixed color, so at U minus V1, like I've done here, and you just consider all the galaxies above this cut, you can trace this red sequence. You can fit, for example, a line which you derive in the local universe, and you trace it as a function of redshift. And this has been done here, which I will refer to the classical method. And this evolution can be expressed within this relationship. We have used different techniques to see if there is actually also a variation in the slope, but we don't find any slope variation for our data set. Interestingly, at high redshift, we already find a large number of very massive galaxies, which are indicated in this plot, which will be very important for the interpretation. Another important goal was really to select different, to use different methods to select early type galaxies. One is the so-called color bimodality using just optical colors. Again, I show you here the U minus V rest frame color for different redshift bins, and what has been studied here is just this evolution in the colors again by making a cut here where red galaxies are basically above this dashed line and other galaxies are below this, and you can trace this evolution, this dashed line again according to this relationship. A second method is the selection by spectral energy types, where you use the whole multi-wavelength photometry, which is here overplotted. So these actually colored histograms are the SCT types, where you can see the red galaxies are again with the red histogram, green galaxies in this intermediate population, and then the blue galaxies with blue histogram. For most, we also use a so-called near UV R selection, where you use near UV colors and R minus E and R minus K colors to select a passive from active galaxies. So what has been done here is that you can distinguish passive galaxies without significant star formation from active galaxies with low specific star formation in this diagram, which is, so active galaxies are indicated as blue, passive as red, and this line which we select our galaxies is perpendicular to the one from the increasing specific star formation rate. So you have galaxies with very high star formation rates located here, galaxies with low star formation rates indicated here, and for most this line is also adopted to trace the overall dust component. So you have dusty galaxies here and less dusty galaxies here. And within this method, you can really select very efficiently these face-on galaxies I've shown in the introduction, which are very dusty galaxies. So one of our major results is we want to trace this red sequence evolution. I show you again what I've introduced in the introduction, the U minus V rest frame color at the fixed luminosity as a function of redshift. As a reference, I just use the Combo 17 sample, which is indicated here with gray, And overplotted in blue are now the Viper's results. So the total blue area you see here is actually the total systematic errors, and the small arrow bars here are just the statistical uncertainties. So overall we find a strong evolution, and that does not depend on which field we are looking. So the evolution is very similar between these fields. And also if we just reject our high redshift point, we find consistent strong evolution. If we go to the right hand side, now the same results are just splitted for the different methods I've been introducing. So the classical method where you have this fixed cut in U minus V colors, and the other methods. And for the classical methods in black, you can see that you really derive only a relatively small evolution compared to smaller evolution than the other methods, which indicates that we are really just tracing the most luminous, the most massive galaxies. Whereas if we go for the other methods, we really can probe the total early type galaxy population, which is not only comprised by massive ones, but also by less massive ones. And this is very powerful. So we wanted to understand our results within the respect of stellar population in modeling. So what I show you here again is this U minus V reference color, the fixed luminosity as a function of redshift, just for one method. And then this gray area is just the scatter, which we have in the observation. And we compared it to predictions from stellar population modeling. So we use the Pegas stellar population modeling, and we start off at high redshift with a strong star formation burst, and then have different star formation histories, different star formation like duration times, which are indicated here with this tau value. It's an exponentially declined star formation, and we have 0.1 to 3 gigareal, different ones. And overall, our data actually suggests star formation episodes in the order of 0.5 to 0.8 billion years. I just show you here two examples of all the models we will be using. So you trace the evolution at this high redshift with this star formation history, and then at the redshift of 3, or for example 2.5, you cut completely the star formation. You need to do that in order to explain this rise in the colors which we see in the observations. That's why you have this upturn in these models. And this suggests actually that we have really a rapid shut-off, a rapid quenching of the star formation at a redshift approximately of 1 within a very short time interval, within about 1.5 to 2 gigayears. After this rapid episode, about 7 billion years, you just have then a very modest evolution. So the stellar population are already in place. You have just a passive evolution with no significant star formation, just the stellar population get redder and fade over time.
Excuse me, how is it related to the star formation rate as a function of redshift, which was prescribed by Puccini and Madao? There was this function, I think it was peaking at the redshift 1, or not?
Yes, what you're referring is the specific star formation rate, and that peaks between 1.5 to 2 in redshift. That is for the total population. Usually these are spiral galaxy samples. So I'm talking here about early type galaxy.
It's completely different, yes, for the spiral galaxies.
So the thing is that, if you want to derive the specific star formation rate, you usually select spiral galaxies because it's easier to measure and you can trace this evolution. What you want to measure here is you want to explain the observational data with the models. So of course you need to restrict the models to a certain set. These, I will show later on that there is some star formation, highly star formation activity for this early type galaxies, but it is just at higher redshift. It's not at this lower redshift. So spiral galaxies have a different evolution than early type galaxies.
So, is this conclusion drawn based on this last point?
No, not only. So,
Yeah, because this is a crucial question whether you don't here see an over-interpretation of data. I mean, naturally your measurements at higher and higher redshifts are more and more delicate because
Yes.
those galaxies are somehow weaker and weaker. And again, if I allow for 2 sigma effect, I assume the error bar is 1 sigma. This point, I mean, the error bar crosses the defeated line, so there is just one point which shows some variation from the previous trend. Isn't it not somehow dangerous to draw such a certain conclusions on just one measurement?
that's why we have also this range in the burst duration time. So even if we just assume a different bins, we still see this evolutionary trend. So it does not depend so much on the binning, and we have a high number of galaxies still. So it's more than a factor of 2 higher than previous studies. So we are pretty confident. We made several tests that we are still complete at this high redshift. So independent evidence for this scenario comes actually from the spectra. So we selected galaxies which are located at approximately 0.5 within the same luminosity range, and also galaxies at high redshift. And galaxies at low redshift, they are really indicated by old stellar population models, by old stellar populations in the spectra, so they don't have any indication of star formation, whereas at higher redshift, there is some evidence for recent star formation available. So that suggests that there has to have some star formation in the past, which we just see still at this redshift. And a third independent evidence comes actually from the number density evolution. So if you count all the galaxies you have according to a certain type, you can derive the number density. This log phi is just the number density evolution as a function of redshift for different surveys. And you see this again in blue. And you see that there's only a weak evolution for all of the galaxies, so that's spiral galaxies and early type galaxies. And then there's this larger drop at higher redshift. If we go to the right hand side, you see the number density evolution only for early type galaxies. You see there's overall a stronger evolution, and there's really this very strong decrease in the number density at high redshift. This is again evidence that we see this really sharp quenching of star formation around this redshift, high redshifts, which is consistent with the result we derive from the color magnitude relation. So for another effect we wanted to study is the color mass relation, where I plot the U-3 rest frame color as a function of stellar mass. And what we see here, very interesting, we already find very massive blue galaxies at high redshift. So you have 3 different redshift bins. This is lowest redshift bin, intermediate, and higher redshift. So at higher redshift you find already very massive blue galaxies. And if you trace now this evolution of this two stellar population, I have roughly approximated that with these lines, you can see that the red sequence actually is frozen with cosmic time, so it does not evolve. So that means that it has to be established at much higher redshift, and it just stays constant. Whereas for the blue population, you see that this envelope actually slightly evolves as a function of time. That means that there needs to be some transformation of blue galaxies onto the red sequence, and most likely that will happen for the low and intermediate mass range. So we have also looked into the morphologies. I give you just a few examples of the morphologies of very massive blue galaxies, and most of these types, they don't show any companions, any interaction, so they are actually undisturbed. And we cannot rule out that some of them have still some low luminosity AGNs or CFT in their central which cause some star formation, and that would, for example, be one scenario that you have star formation in the center, which then rapidly gets quenched again, for example, through AGNs, and then these galaxies can evolve from the blue cloud to the red sequence. So, some time ago, Soom-Toft and collaborators introduced this scenario of early-type galaxies. So I come back to your question, where you start off at the Big Bang, and then you have different phases in the evolution to come up with a massive early-type galaxy. So you have some merging activity at a very high redshift, redshift of 6. Then you have some star formation activity, which is usually hidden because there's a lot of dust involved. So it's this dusty starburst galaxy. You have a quasi-activity, so you have an center AGN. And then this results in a compact remnant galaxy. And in the last part of this evolution, you have some merging activity, and that you finally come up with the local galaxy. So with Vipers, we can mainly probe this range from local redshift up to redshift of 1.5, and we come up with a slightly different picture where we actually see differences in the masses of the galaxy. So we see a different evolution for high massive galaxies compared to low massive galaxies.
Excuse me, where's the place for spirals in this diagram?
It's not here actually, so it's just restricted to little galaxies. Yeah. So there are many predictions for different types of galaxies, and it's you cannot combine, unfortunately, all that simulation in one plot. It's too complex. Yeah. So I would like to stay here for this interpretation. So I've shown you from the stellar population modeling that we have this rapid quenching and star formation, this rapid buildup of the sequence, which is supported by the number density and the star formation we find in these high redshift galaxies. And in addition, very important, we find actually evolution in the scatter of the color magnitude relation, which means that we find a decreasing scatter as a function of cosmic time for bright galaxies, whereas the scatter in the color magnitude relation for low massive galaxies remains constant as a function of cosmic time. That means that for high massive galaxies you have some merging activity at high redshift, and then this quenching of star formation, but no merging activity from redshift of 1.3 onwards. You just have this just a fading and a slow evolution of the stellar population, whereas for low massive galaxies you actually have some additional wet mergers, which is just mergers with star formation involved. And we think that this can happen in galaxy groups, because in galaxy groups these physical processes are more accelerated, and also this quenching can happen at much more shorter time scales, so you can really quench that much more quickly. And then you might end up with some residual star formation, and you could still have some limited amount of mergers, which has been predicted, but not too many, in the order of 0.7 from redshift of 1. And within this scenario, then you can really build up the low mass and the intermediate mass end of the color magnitude relation. So I come now to my summary already. So I've shown you that we find not only massive red galaxies within our survey at the very high redshift 0.7 to 1, but also very massive blue ones. We find this so-called environmental dependence in the scatter of the color magnitude relation, which is different for high luminosity galaxies than for low luminosity galaxies. And we don't see too many differences how we select early type galaxies based on our different selection criteria, although we find for very popular studies like the classical definition, where you just have a fixed cut in U minus V colors, you really probe the most massive galaxies, and you just are restricted to a certain population, and we don't find a significant evolution of the dust content in our galaxies. So for the buildup of the red sequence, I've shown you find this rise in the number density evolution since redshift 1, and we have this really rapid quenching of the star formation at redshift 1, which builds then up the red sequence within this very short time interval. Whereas for massive galaxies we have only very limited amount of mergers, where we get independent support from the spectra and also the resulting luminosity function and mass function. Whereas for lower mass galaxies, really there is some additional merging activity necessary, which can be then enhanced in the group environment and build up this low and intermediate mass hand of the column magnitude relation. So now I would like to show you that this is just one of these projects I've been currently working on. This was Vipers. But in order to understand galaxy evolution and galaxy formation, you cannot only restrict yourself to one type of galaxies. You need to actually consider the whole galaxy population. This can be done in two different ways, via service like Vipers, or in the future Euclid, using statistical samples, so large sample of galaxies in the order of 10,000 or more. But at the same time, if you want to understand the physics, you need to have smaller samples of where you really study in detail their structural appearances and their spectral properties, which I've been using here. Three different surveys: Clash VOT, then a sample of clusters with low X-ray luminosities, and then some strong lensing groups. And all these projects are aiming, of course, to constrain the major questions. So, what is dark matter? How is dark energy? When does that happen, and how can we explain that? And what is, of course, the contribution of variance? So I will just give you some of the highlights I've been currently working on. One is gravitational lensing. So you see here just a very nice example of a galaxy cluster at redshift 0.2, so about 2 billion years ago, and you see very nicely these gravitational arcs. And as many of you already know, in general relativity, you know that light gets deflected by dark matter, which is just indicated in this scheme here. You have a very distant galaxy, you have Earth here, and you have a galaxy cluster here. And due to the dark matter of these galaxy clusters, light gets banded through the wave from the distant galaxy to the Earth. So there are different methods of lensing depending on the symmetry and the appearance where this distant galaxy is. So according to the symmetry of the system, you can distinguish strong gravitational lensing, where I give you here some very nice examples from Hubble Space Telescope imaging, where you have these very strong gravitational arcs. So this galaxy gets actually distorted, and you have this very nice arcs structure. The most prominent if you have, for example, a almost complete Einstein ring. Weak gravitational lensing affects then smaller scales, mainly then the sizes of the galaxies, where the sizes of the galaxies get slightly distorted. And the smallest scale is then microlensing, which then affects, for example, the light from stars or within our solar system. Of course, we want to understand really what dark matter is by studying gravitational lensing. So the projects I've been working on, I am leading a project where I'm observing in total of 4 galaxy lensing groups at low redshift, 0.3 to 0.5. So you have one example with very nice gravitational arcs again. So we combine again multi-wavelength photometry and spectroscopy. You need a spectroscopy, for example, if you want to measure the total mass within a certain radius, where you can derive the circular velocity from the spectra. And this is just an approximation for one model, the single isothermal sphere. And another project I've been working on is the Clash VOT, where a Clash stands for cluster lensing and supernova survey with Hubble. So it's actually a proposal to study supernova in distant clusters, but we have a follow-up project with the Very Large Telescope to get spectroscopy for 14 of these clusters. So again, the main scientific goals are to study dark matter on different scales, so on the mass scale of galaxy clusters, groups, and individual galaxies. There are also other science topics. You can have higher redshift objects, or you can also probe the reionization of the universe by discovering very distant galaxies. And for the future, I really want to work with Euclid. I'm a member of Euclid, which is an ESO M-class satellite, which observes and really pins down maps and the geometry of the dark universe. So it studies dark matter and dark energy on different scales again, from galaxies over groups to the large-scale structure. What you really want to probe with Euclid is what has been also given the Nobel Prize last year for the acceleration due to dark energy. So it's some of the highlights. So for strong galaxy lensing groups, this is an ongoing project. I give you just very nice examples here. You see different gravitational arcs depending on the mass of the system. So very small ones, but also larger gravitational arcs. And we are currently getting follow-up spectroscopy that is necessary not only to get the redshift, but really to get the kinematics, so that you can derive the velocity of the stars in these galaxies and then derive the total mass distribution. And very nicely, recently we have found an emerging galaxy strong lensing group, which we call the bullet group, which you can see here very nicely. For the first time, you could separate actually the X-ray gas from the dark matter and the baryons in the system. So you have the X-ray gas in these contours in cyan, which is actually displaced, where the center is here, from the central mass distribution probed by strong lensing and the baryons, which is here indicated by the white contours. And we find this separation is in the order of 124 kiloparsec. This is very exciting because it's for the first time a measurement at this mass scale. So the mass of the system is 2 times 10 to the 14, which is a factor of 2 smaller than the smallest mass scale which has been probed previously. And compared, for example, to galaxy clusters, this is a factor of 7 smaller than galaxy clusters. So you really can probe now with these techniques smaller systems. And for Clash VLT, I want to give you one example where you can probe the mass profile of galaxy clusters. So this is the mass profile as a function of cluster-centric radius for different scales. So in the inner parts, you can really pin down this mass profile by a strong gravitational lensing. In the outer parts, you can measure again the kinematics of the galaxies, and you can trace the outer parts. And in between, you can combine it with a third independent method with weak gravitational lensing. And by combining all these 3 different probes, you can not only measure the total mass in dark matter, but you also can split it into the different components. You can probe the gas component, the stellar mass, and the mass locked up, for example, in this brightest galaxy cluster in the center. Here is just shown how this will be done. So you have the total mass probed dark matter and baryons, which you then can split to the halo mass, which you derive from simulations in the dark matter, and then you can also measure the baryonic mass locked up in the stars. And of course, very nicely, you find interesting dropout galaxies like these high redshift galaxies, where we find here this very strong Lyman alpha emission at a redshift of 6.11. And this system actually split up in 5 different individual galaxies. So very interesting topics. And finally, I want to show you what can be done with Euclid. Euclid will be able really to measure dark energy, and there's a very powerful method we recently described in one of our white papers, where you can use gravitational time delays, so strong gravitational lensing tools, to measure a time delay. This can be done by measuring the photometry of a variable source, so a quasar, as a function of several years, in the order of 5 years. And by measuring this time delay, you can derive this time delay by assuming a mass profile of these galaxies and then you can measure this time delay between these observations, you can derive the Hubble constant to an accuracy in the order of 6 to 7%. So far, this technique has not been established for many sources because you need a long observational campaign to do that. But of course, with Euclid and LSST, you can get in the order of 10,000 of quasars in total, and probably you can follow up in the order of 100 of them with multi-wave band photometry. And what you can really then do is you can simultaneously constrain the equation of state, dark energy, the curvature, and also the Hubble constant. So you can see here what the predictions are if you use WMAP, this kind of time delay technique. See that the contours gets much smaller and much more tighter. I'm actually also proposing to select this huge sample using automatic techniques with Dr. Katarzyna Małek. She's an expert in SVM and other automatic methods, and I think this would be a very powerful approach to use her technique. And finally, I want to show you that for these detailed studies, you really need to combine this high resolution photometry from HSD. You need to also have deep spectra and multi-wavelength photometry. I'm currently conducting a survey investigating 200 galaxies in different clusters, which is called the Stellar Population Environment Survey, so in different environments, different cluster environments. Then I will actually double almost the number with Clash VLT. Like I mentioned, we have also kinematic data for that. We can do the same studies using a much larger sample. And for the future, I'm actually involved in a future instrument in the science case and also in the survey development of WEAVE, which is an optical fiber spectrograph at the Wilhelm Herschel telescope, at a 4.2 meter telescope. And there you really can measure the total cluster population for the first time at this intermediate redshifts. So you can show you one example, so this high resolution HSD imaging, and for these galaxies we obtain a very high signal to noise spectra. You can see different stellar population, which you then can compare to stellar population model predictions, and you can then derive the chemistry of all these galaxies. So with further ado, I will leave you with the most detailed view in the universe from Vipers. So dziękuję bardzo.
On these spectra, there are characteristic drops. For example, the last one. Does this have any physical explanation? When you follow the spectrum, there are
This drop?
Yes, it goes down. It goes down significantly at 3 places.
Yes.
First,
this is a characteristic structure of the spectrum.
Yes,
So-
but does it have a physical explanation why the spectrum drops down at this particular wavelength?
Yes, this is due to the overall properties of the galaxy. So
But
this
is this characteristic for all galaxies, or
no, this is characteristic for early type galaxies. So spiral galaxies have a different shape of the spectrum. I have one example here. So this is a spiral galaxy sample as for spiral galaxy. Of course, at higher redshift, but usually spiral galaxies have a much flatter continuum and strong emission lines. Yeah.
Yeah, but
So the shape
here
here
there
is
are no strong emission lines, right?
right because it's an
But still there are,
elliptic galaxy.
there are these drops.
Yeah,
So
these
does
drops
this
are-
mean
yes.
some?
These drops, okay. Yeah, these drops are actually due to the chemistry, due to the stellar population. So
And is
these are
this-
characteristic for different elements. And this is what we want to measure. We want to measure the different elements, which you can only obtain if you have a high signal to noise spectrum. So
But this looks pretty good. So
Yes.
can one explain why this drop occurs at this particular wavelength? What is the physical process that could here explain?
It is not so easy to
This
say
is-
that
it
one
looks
element
like
causes. Yes.
Looks like absorption. Absorption.
Yes. No, it's an absorption due to a chemical element, but it's difficult. This is very difficult to then distinguish or to derive the physical mechanisms. So different, currently we can measure these element abundances in the spectra, and what usually is been what we can do currently at this stage is that we combine different element abundances and then derive the overall ages of the galaxies and the metallicities. These are some major parameters we can derive, and we can compare that to stellar population models. But we are way far away that we just measure one element abundance and trace that to a physical mechanism. That is unfortunately not possible yet. Because
So when you compare the spectrum from different galaxies,
yes.
then there is no regularity here.
Well,
That this drop occurs at the same wavelength for...
no, at the same wavelength, yes, but
So there must be some physical process that explains this drop.
yes, but we can. The simulations are unfortunately
No, the simulation, this is observation.
yes, but
Why
I don't have any physical explanation why these drops occur at a certain time. I can only analyze the whole spectrum. Different element abundance ratios give me different indications, but it is very difficult to say that this element abundance ratio causes this physical mechanism, because the physical mechanisms are more globally, so what you can do is, of course, if you want to compare this spectrum with a spectrum you obtain in the local universe, you need to account for observational effects. So if you obtain here a spectrum, then for example, it covers a much smaller range in the galaxy, because the galaxy is much far distant and you just probe only a small range. So of course that needs to be corrected when you compare that to local measurements, which has been done.
Can you measure the metallicity, for instance? What is the
Yes.
metallicity with respect to the solar?
Well, these are
Similar
subsolar metallicities, so they have much lower metallicities. The main,
-2 or something, yes?
yes, so what you want to derive here, the stellar composition is mainly the ages of these galaxies from these different element abundance ratios and the metallicities. Currently, the problem is that you measure all these indices, but you don't have any models to constrain that. So, I mean, I have these measurements, but it's very difficult for an observer then to say, okay, I get this very nice element, but I need some explanation for that. And this is a very complex, still a very complex topic. This has been done very extensively in the local universe, but at High-redshift it has never been done, because you need really very deep spectrum. You need observations in the order of 8 to 10 hours for these redshifts. So at look-back times of 4 billion years, if you want to have this nice spectrum, you really need to observe for 8 hours on a 4-meter telescope, which corresponds to about 2 hours at least at a very large telescope. So
This is expensive.
is it expensive? Yes. But it would be very interesting, really, to say this element can cause this physical effect, but unfortunately, this is only possible, hopefully, in the future.
More questions? No, thank you very much.